next games. We are fine on track, and that implies that we have now the pleasure to listen to Tobias Graf and Marco Platzner. They again, and I can say again, managed to write a very good paper. As you know, we since a few years we have also a procedure for the best paper award. Sometimes it is clear, sometimes it's not so clear. Last year in Yokohama it was a tight first place, as you know, because we have sometimes places, and one of the, I would say the half of the tight place is also now in front of us. So congratulations with now convincing everybody that in fact that prize, I would say, in Yokohama was only a stepping stone for your success here. We also talked about not only the 12 pages which we could publish in the LNCS. The authors were prepared also to, I would say, give an expanded version for the ICCA journal, so you could see everything that you will hear now also soon, I would say within a half a year or whatever, this I would say or either September or December in the journal, and that's fantastic. I would like to shorten my own speech, so I give the floor to you. Also introduce yourself with your affiliates and whatever you do, because that's good. Sorry. Yes, okay, we apologize for not giving already you an applause up front, because now thank you for being here and giving on the first day of the conference.
Yes, thanks for the nice introduction. So my name is Tobias Graf, and we wrote the paper together with Marco Platzner. We're both from the University of Paderborn. So let's just start with the paper. It's about adaptive playouts in Monte Carlo research, and we use policy gradient reinforcement learning. And yeah, basically that's all to say, but now some more details about what we do. So I decided to give you some introduction with examples which already use the adaptive playouts. So why we want to do it? In Go we always have some position, and the playout policies are not always perfect, and some areas on the board are just misevaluated. So this is a position from Rémi Coulombe's presentation on criticality, and in the top left corner, see this? So in the top left corner, the playouts misestimate how the territory is at the end of the game. So our players give this black territory, but it's white. So what we want to have, this is what the static playouts give. We want some learning mechanism so that the playouts correctly evaluates is to be white territory. So here's another position. I think Ingo already knows it. It's from a match between Crazy Stone and a strong German player. And in one game in the top left corner, again, there occurred a position where our playouts give a 50% ratio for black territory, and if you adapt the playouts, you get the correct evaluation of black being dead in the left corner. And the third example, in the last conference in Yokohama, Shi Chuang had some paper on the two safe groups test set, just to see how programs evaluate these positions. And the idea is to have two white groups on the board which can easily die in the playouts, and the Monte Carlo research has really difficulties to handle these. So if the playouts do not understand it, it's really difficult for the program to evaluate this correctly. So our players do not understand these, so this is what the static playouts give. So the bottom group dies in 80% of the cases, and even the top group is not safe, really safe. And if we run adaptive playouts, then the playouts can learn that the top and the bottom groups are alive.
The top white group is alive?
What?
The top white group is alive?
Yes.
I can't see how.
Maybe we can discuss later with a stronger player than me. So
and the Monte Carlo usually shows it dying.
Yes, the Monte Carlo usually shows it dying, and if you adapt the playouts, it will be alive. So how do we do it? So this is just a rough overview of the paper, so please read the paper for all the details. So we use the softmax policy. It's the same as following a Bradley-Terry model, if that is a more common name for you, or the Gibbs sampling, which Tristan Cazenave just named. This is a softmax policy. So for each move A in a position S, we assign a probability, and we have weights theta and features phi for each move. And the numerator is just the normalization to have this as a correct probability distribution. For example, for features you can use 3x3 patterns or locality, so near to the last move, or some semi-features when at this binary indicator is used in the features. So if you use binary, then the product between phi and theta is just summing up all the weights where the features are 1. The advantage of such a policy, for example, difference to a Mogo style or so, is that it's differentiable, and so here just put the gradient of the log policy, which can, for example, be used to fit the policy to a log likelihood of some professional players or so. So you can learn this policy by following strong experts. And now we want to have this adaptive softmax policy. So we just split the weights in the features in a static part and an adaptive part. So we have a static bar theta and an adaptive head theta. So the static weights and features are learned offline before we use the Monte Carlo tree search. And the adaptive weights are set to 0 before the search, and then they can adapt during the search. A simple example, which you also use in the paper, is to use features which are position independent for the static part, and use the same features for the adaptive part, but use them in a position dependent way. So the 3x3 pattern position independent means it matches everywhere on the board, and position dependent means for every point you look which 3x3 pattern could occur there. This just adds more flexibility for the adaptive players to learn. So how do we do it? So this is the whole paper in one slide. So it's based on policy gradient, or also known under the reinforced algorithm. So the performance of a policy, so the average reward you get, is the result of the game and the probability of the game under the policy you have. And then you just sum over all the games. And then this is the average reward performance metric of a policy. And of this function, you can take the gradient, and you find how to do this in the paper. So the result is that if you sample games according to the policy, then you just have to sum up the gradient of the log policy. So this is this here, and just multiply it by the result of the game. And if you do it several times, you get an unbiased estimate of the gradient. So how often you do depends on the variance. We just do it once. So we sample one game, and then you get an estimate of the gradient, how to improve, to increase the performance of the policy. So this is basically the policy gradient. What we add here is some regularization to the adaptive weights. So we start by 0, and we already have a policy which is quite good to estimate, and we don't want to drift the policy too much away from our good policy. So we just penalize in the last term by an L2 regularization, which is quite common in machine learning, just to avoid the policy to overfit to current positions. And second, you can add a baseline to the policy gradient algorithm to decrease the variance of the estimate. So we just take one sample from the expectation. So there are some measures in the literature to reduce the variance, and the easiest one is just to use the average results of all the games. So this is what you can here do. So you just take the result of the game, subtract the baseline, and then multiply by the sum there. And yes, if you have this, you can just use stochastic gradient descent to optimize the adaptive weights of the policy. So that's all on math today. So how to integrate it into MCTS? This is the standard MCTS part. In the top we just expand the tree. If a state is not there, then we select the move by UCB, and then either we run a playout or go further down the MCTS tree and finally update it. So where is the policy gradient update take place? So instead of the playout, we have to measure the gradient also during the playout. So we don't only have a result, but also the gradient. And then we do the policy gradient update of the last slide with the stochastic gradient descent with the baseline B. And the baseline B is the average reward. So we use in the Monte Carlo tree search, we just use the average win rate in the state, but for the baseline. But to make it more stable, we only use it once a state has more than 32 visits. So if the state has less than 32 visits, just the baseline of the previous state in the MCTS search is used for a baseline. Yeah, the results. I already showed some results in the introduction. So the first one is the speed. So we heavily optimized it, and the baseline is the static version without any adaptivity. And if there's one thread, we have a decrease to 84%. And we had a simple solution for parallelization only. So when the playouts are run in parallel, we all have to update the weight vector, and we just made one global mutex on this. So there's a lot of log contention during the policy updates, which you see when you increase the number of threads. So the performance goes down to 68% regarding to the optimal to the static version. So there's a lot of room to improvement. And then we measured the playing strengths. So in the top of the table you see results for equal number of players, and in the second for equal number of time. So we run games against Pashi, a strong open source program, and about 1,000 games. And yeah, you have to look at this maybe in a couple minutes. So what you see is that on equal time, we have about 130 ELU plus to Pashi, while the static is slightly decreasing. So when we increase the number, the thinking time, Pashi gets a lot of stronger, and we are about even to Pashi at this point. But with the help of adaptive playouts, we have about 130 ELU points in improvement. And here you see the difference. It's just very, very slow. So if you have the equal number of playouts, then we have 320 ELU towards Pashi, but this does not include the time you need. First, our playouts are slower at all, and then we also have to adapt them, which makes them even slower. So in an optimal way, we would have 300 from the quality, but because of the time used for this, we only have 130.
So static means just regular MCTS?
What?
Static means just regular MCTS? The static result, is that just regular MCTS? Without the...
Without adaptive, yeah.
Okay, and...
The static means the playout are not adapted during the search?
Just plain old MCTS, basically.
It's just basic MCTS. Yeah, not basic MCTS, but the static version.
Okay. And how many nodes per second were you evaluating? About?
Okay, you can see it maybe here. This is a 16 core, so here we are using the 16 core versions. So in 1 second, you can see it's about 13,000 for the adaptive and close to 20,000 for the static one. So running on 4 seconds, it's about 80,000 for the static, and a little bit less for the adaptive.
On 19 by 19.
On 19 by 19, yes.
Wow. Wow.
So the players are really strong. The programs are already quite strong in the experiments.
Yeah.
So this is the playing strength. And I also tested on the two safe groups. I also already introduced in the introduction, just for a reminder, some test case. So we have two white groups, and our players don't understand it. So Zen does, but we does not. So what happens is, here you see a subset of the first 9 test cases. Here's a number of iterations in the MCTS search. So we start by 1,000, this is block scale, up to 1 million here, 2, 4, and so on. Up to 60 million playouts, we just check the evaluation at the root node in the Monte Carlo tree search. And this is the win rate. It's, for example, here 80% for black. And all the positions are designed to be a win for white. So the winning rate basically should be 0 in a perfect. And in the test cases of Shi Chuan, he decided to make some barrier on 0.3, so 30% winning rate should be a target for a good Monte Carlo tree search to reach in these positions. And you see that the Monte Carlo tree search cannot deal with it. So this is for the static playouts. And once we use adaptive playouts, the winning rate just decreases towards 0. So the playouts learn how to deal with these true safe groups, and then somewhere here after some time, they know that the groups are living, and then they can converge towards 0. What strangely happened in one case is test case 2. At some point it decreases and then it goes up. So I asked Shi Chuan if this position is correct, and he really stated that this was a mistake in the test case. So this position is the win for black. So you can read the idea in the paper. So there's some co-fights involving both groups, and then black just wins by capturing a group of them. So this just can.
But it still went down first. So
what?
It still went down first. So it was tricky for the.
Yeah, it just has to learn that in the beginning it thinks both groups are captured, and so it just.
How long did it go before going back up?
So about here it starts.
Oh, okay.
So the search just has to know that, well, when you play normal moves, both groups are alive. So this is something it has to learn before it can see, okay, there's a move when this does not happen. So it first has to adapt, and then it can see, okay, there's a special move which can kill, and I am winning. Yeah, and this is the second part of the test case. Again, we see there's not much improvement. So either they just stay. So even if you search for a long time, and 60 million playouts is a very long time to search, then they do not make much progress. And unfortunately for the adaptive playouts, we don't see any progress as well. So there are positions which can be handled by the adaptive playouts, and there are positions which cannot handle it. So this is one position to show why some cannot handle it. So this can come up in some test cases position, and again, white is alive. So
and white is to move.
Black is to move. And the static playouts get the evaluation correct, but once we adapt them, they get it wrong. Why? The problem is that black has 2 attacking moves, which you see here. The adaptive weights are increased for these moves, so black learns how to attack this white group here and here. And once black plays here, white has to play here, and if he plays here, white has to play here. But the features of the playout policy only have the 3x3 neighborhood, so they don't have the representation to learn which defending move has to be played. So there's a general trend to increase the weights of the defending moves. So yeah, they are good, but the policy don't know which one is good in a position. So that's why.
So it thinks too locally.
Yes.
Okay.
So if there would be some feature which would be, okay, the last move was an attacking move to this one, then they could adapt and learn it. But yeah, this just shows that it depends on the features which you use, if the policy can adapt or not. And unfortunately, it can make playouts worse. But as you have seen in the playing strength results, the overall effect is that they get stronger.
Can you increase the look window to beyond 3x3?
Yes, but how much?
Yeah.
Yeah, it depends. So here it would be easy just to increase it by 1, add some feature, but the larger the pattern is, the more information you need to learn, right?
Yeah.
This would be a problem. So yeah, it's quite good for programs which already have a lot of features. So the more features you have in the playout, the better they can be adapted. Yeah, as a summary, we adapt the playout policy in the Monte Carlo tree search. We do it during the search, and we want to fix the wrong knowledge we have in the playouts. And we do it by the policy gradient reinforcement learning algorithm. The slowdown is there, but it is acceptable. We got a strength improvement on equal time by about 100 elo, and we got a large improvement in the 2 safe groups test set. Yeah, and future directions would be to improve the performance, especially a better parallelization than we did. Everything depends on the features. So the advantage of the algorithm is that it doesn't rely on any specific features. So you are free to design new features which you think are better or better suited to your problem. So which features are good, and maybe we can either learn them during the search, or we might use neural networks to adapt. We could also use other policy gradient algorithms. We use a very simple reinforced algorithm. They are much more complex actor-critic algorithms, which might be an option just to speed up the learning. We do stochastic gradient descent. We have to set a learning rate, which is not that easy in the tree search. So what's a good way to do this? And how good does MCTS deal with adaptive playouts? So in our experience, it's not well suited to this. So usually you have results of the playouts drift because of the search, and now there's another drift in the adaptation, and this really makes the search sometimes unstable, because it cannot just find a good move, then it adapts, and then maybe even plays a very worse move. So the statistics are not that well suited. So there's some improvement needed to even take more advantage of this method. Yeah, that's all. Thanks for your attention. Any questions?
Ingo.
Was your investigation for board size 19 × 19 or for smaller boards?
Mostly on 19 by 19, but the 2 safe groups test set, for example, was on 9 by 9.
And did you apply this adaptive policy in the tournament yesterday?
Yes.
And what was?
Silver medal. So, yeah. But yeah, it really depends. So you saw it is a 100 elo improvement. So this is just realistic. So we are about 3 dan on KGS, and without it would be about 2 dan, and I think Fan is 6 dan or so. So yeah, you know who won the tournament.
What is the secret of Zen, you said?
I'm the wrong person to ask.
Zen was the gold winner, as you may understand, for a thing, and he said the silver medal. So we are always interested in why the other one is better, as you understand. And the answer, as I now may, I would say, derive from your, I would say, quote, is that they have expert knowledge in them.
Yes, I think they have a lot of expert knowledge in the policy, just to do it right from the beginning. So we have first to adapt to the position, and then sometimes it works with the feature, sometimes it's not. And of course, if you have the knowledge already there, then yeah, you don't have to adapt.
Yes.
But I would say even then it's quite an advantage to adapt, because even there are always some mistakes, and the policy adaptation would fix these mistakes, so even makes them even stronger.
I understand that this was in normal life, everything you know, you have not to calculate anymore. So that is
Yeah, that's true.
Yes. Next question.
Yeah.
Yes.
What is the name of your program?
Abacus.
Okay. Third question. Then, if there are no third questions, then I give the floor to Lynn. Lynn, what's your next question? You are out? No, that's impossible. Yeah. What are the names of your programs?
Yeah.
Call them all 5.
Yeah, I'm doing Surakarna, lines of action, drafts. I don't remember. Faber. I did Einstein yesterday.
Yes.
I don't even remember.
That's a good example for you. Yes. Okay. Thank you.
Yeah.
Last question here on outside the winner of the best paper award. If there are no questions, then I would say, could you imagine what is the essential thing you communicated to the referees that they were so delighted on your paper?
I don't know. Still I'm the wrong person to ask. Maybe you should ask that. Yeah, I think it's just that it works. So there are a lot of stuff on Go, and I think the essential thing is to combine the knowledge you have from the playouts with the new knowledge in some convenient way, so that you do not destroy this knowledge you have by the new knowledge you learn. So this is, I think, the essential thing why it works.
Yes, I must say I also asked myself when I listened again to your story that what is now essentially new in it, yes, because you are, I would say, an expert in combining all things we more or less know or which are familiar to us, but I think that the essence of your contribution is the right tuning of the things, and that is always, was in computer chess also difficult point always. We remember the papers of Jonathan Schaefer, who gives an overview of all kinds of techniques he could use in his program. Well, then the difficulty was always when to use what technique, and that's in your case also. So that's my translation of your performance here. Is that okay?
Yes.
Thank you very much. Then it is now time. Yes, Todd. Oh, yes.
So, if I'm understanding things correctly, Richard started out by talking about advocating a very simple play-out policy that cuts short early termination.
Yes.
And the following 2 talks are essentially about adapting a smarter play-out policy.
That's so. That's so.
So, can any of the authors try to characterize which types of games, what characteristics of games benefit from a smarter adaptive play-out policy, and which ones you shouldn't bother?
Okay. I give them all 3 for 1 sentence a line. Richard, you first.
I find that early playout seems to benefit most situations, so I think most programs can benefit from it.
But it could also happen, of course, that you only reach, I would say, silver medals. Although you are now congratulated with the gold medal, eh?
Yeah.
Yesterday, yes.
But and Havana is a good example of that. Havana seems to have peaked. And
Yes.
so the question is, now is that, have I reached the limit, or do we have to improve the playoff policy? And I don't know the answer.
Yes.
Yeah. That's
Tristan.
For me it is simple, it's miser games where adaptive playout works much better than in other games.
Yes, but if you look at miser games, yes, you may understand what is the essence of a game. The essence of a game is that you try to win. For instance, with Victor I discussed many times on the essence of the game, whether I would say Connect 4 at that time was a win or just not. And that was it. And of course, games are only interesting if you cannot predict that it is a one game, and that is just that's the point. And then there are only few pots which lead to the win. If you reverse that game, then you should not be surprised that the inventor of the game, there are many losing moves. Of course, then there's the best losing move, but I would say the amount of losing moves is abundant with respect to the amount of winning moves, as you may understand. So that changes the nature of the game completely. I'm not completely sure in what sense and how you could exploit this change of nature, but that is another challenge, so to speak. So I was not surprised on, I would say, your remarks and on that result.
But both players have an abundance of losing moves, right?
Yes, that's true. That makes it again an interesting game. That's absolutely true. Yes. Yes. You're the last one to comment on this.
I think that it will work best on games like Go, where the board doesn't change so fast. So If there's some sub-games or some areas which are more or less static, then the policy can adapt to them quite fast and good.
Okay. To collect the, I would say, the sessions in, I would say, a harmonic order. That implies that we set together which belongs together, and even we try to give an order in it. And for the first session, I would say, worked out very well. We have two more sessions. We have two sessions of two lectures hereafter. We start at the 10:15 again, so the break, the coffee has just arrived. I would like to mention your attention, Lynn, also for you, the attention, yes. That is tomorrow we start at the 8:15. Yes, you will not come later, but then you know at least, then you don't miss anything, yes? Okay. We now have coffee. We only have coffee as a drink. We have and tea, no other things, but anyway, I hope you find something